Welcome to Sri Learning Academy. Let's simplify types of operating system. When we talk about operating systems, we usually imagine something like Windows or Android. But in reality, there are many different types of operating systems, each designed for specific purposes, devices, and workloads. The kind of operating system you find in a smartphone is very different from the one running a space shuttle, a bank's mainframe computer, or even a small sensor on a smart light bulb. So in this part, we'll explore the different types of operating systems, how they work, where they're used, and why they're designed the way they are. Let's start at the top with the giants of the computing world, the mainframe operating system. Mainframes are large, powerful computers used by big organizations. Think of banks, government agencies, insurance companies, or airlines. These machines handle thousands of tasks at once, often from hundreds of users spread across the world. The operating system for a mainframe must therefore be highly reliable, secure, and capable of managing massive workloads simultaneously. Imagine an airline booking system where thousands of passengers are checking flight availability or booking tickets at the same time. The system cannot afford even a single minute of downtime. Operating systems like IBM's RTOS or Unix-based mainframe systems are great examples. They are built for throughput, meaning they focus on handling as many jobs as possible rather than making one job finish fastest. A mainframe OS supports batch processing, transaction processing, and time sharing. Batch processing means it can process large volumes of data in groups, like clearing all banking transactions of the day at midnight. Transaction processing means it can handle individual requests, such as a single ATM withdrawal, accurately and instantly. The key idea here is reliability and scale. If a personal computer crashes, it's an inconvenience. But if a mainframe system goes down, an entire bank could stop functioning. Moving down a layer, we come to server operating systems. A server OS is designed to serve multiple clients. These clients could be other computers, users, or even applications over a network. If you've ever opened a website, downloaded an app, or used cloud storage, you were indirectly communicating with a server running one of these operating systems. Examples include Windows Server, Ubuntu Server, Red Hat Enterprise Linux, and CentOS. Unlike mainframes, which are huge centralized systems, servers can range from small local servers to global-scale cloud servers. They manage network connections, user requests, file storage, and databases. A web server might run Apache or Nginx to handle websites, while a mail server could run Postfix or Microsoft Exchange to manage emails. A key feature of server operating systems is stability under continuous load. Servers often run for months or years without rebooting. They also prioritize security and resource management, ensuring that no single user or process can take down the whole system. For example, think of a school website. The server OS manages requests from hundreds of students logging in, downloading forms, or checking grades. It ensures that every request is handled efficiently and that sensitive student data is protected. Next, let's talk about multiprocessor operating systems. The name sounds technical, but the idea is simple. These are operating systems designed for computers with more than one processor or CPU core. Modern systems, from laptops to supercomputers, often have multiple processors working together to speed things up. A multiprocessor OS ensures that all these processors cooperate efficiently. It distributes tasks, balances loads, and synchronizes access to shared memory. Imagine your computer's brain is split into 4 or 8 smaller brains, all working together. The operating system acts as the manager, deciding which brain gets which task. For instance, when you're gaming while also streaming and downloading a file, a multiprocessor OS makes sure one processor handles game graphics, another manages network operations, and yet another deals with background downloads. Systems like Windows 10, Linux, and Mac OS are all capable of multiprocessor support. In high-performance computing, systems like Unix-based clusters use many processors, sometimes thousands, to handle massive scientific calculations, weather simulations, or AI training. The goal is clear: better performance, faster execution, and efficient use of hardware. Then we move to something more familiar, personal computer operating systems. These are the OS types most of us interact with every day. Whether you're working on a laptop, a desktop computer, or even a home workstation, your OS falls under this category. Personal computer operating systems are designed for single users or small groups of users, offer a friendly interface, and general purpose functions. Examples include Microsoft Windows, Apple's Mac OS, and various Linux distributions like Ubuntu or Fedora. These systems focus on ease of use, flexibility, and supporting a wide range of software. You can write documents, browse the internet, play games, or design graphics all on one platform. They also manage peripherals like printers, cameras, and USB drives. What makes them unique is their graphical user interface GUI, which allows users to interact using icons and menus instead of typing long commands. So while mainframes focus on reliability and throughput, personal operating systems focus on usability and versatility. Next, we move to smaller devices, handheld computer operating systems. These are designed for devices that fit in your hand, such as smartphones, tablets, and PDAs. The main challenge here is that handheld devices have limited resources, like smaller memory, lower processing power, and battery constraints, so the operating systems running on them must be light, fast, and energy efficient. Examples include Android, iOS, and HarmonyOS. These systems manage touchscreen input, sensors, mobile networks, and app permissions. Think about when you switch from using your laptop to your phone. On your phone, everything feels simpler, apps open instantly, touch gestures replace the mouse, and notifications keep you updated. That's the design goal of handheld OS, a smooth, responsive experience on limited hardware. Another interesting aspect is connectivity. Handheld operating systems are built to constantly stay connected through Wi-Fi, Bluetooth, and cellular data. They also integrate with cloud services, so your data is always in sync across devices. Now, let's talk about embedded operating systems. You might not see them directly, but they're everywhere, inside microwaves, washing machines, smart TVs, and even cars. An embedded OS is designed to perform specific predefined functions, often on a dedicated piece of hardware. Unlike general-purpose systems, they don't need to handle many tasks at once. For example, the operating system inside your washing machine controls the motor, water levels, and timers, but it doesn't need to browse the internet or play videos. Embedded systems are usually small, fast, and highly reliable. Examples include VxWorks, free RTOS, and even small versions of Linux like embedded Linux. In cars, embedded OS helps control things like anti-lock braking systems or airbags, where timing and accuracy are critical. The main idea is that the OS is built for a very specific purpose, and every part of it is optimized for that purpose alone. Another type that's closely related is the sensor node operating system. These are even smaller and simpler than embedded systems. They run on tiny sensors that collect data like temperature, motion, or humidity and send it to a central system. You'll find them in Internet of Things IoT devices, smart agriculture systems, and environmental monitoring setups. Because these devices have very limited memory and power, their operating systems are extremely lightweight. Examples include TinyOS, Contiki, and Riot OS. For instance, in a smart farm, hundreds of small sensors might measure soil moisture and send updates wirelessly to a central controller. Each sensor has its own mini operating system that ensures it can communicate, save power, and transmit data efficiently. The focus here is energy conservation, minimal resource use, and reliable communication. Now we come to one of the most fascinating categories, real-time operating systems, or RTOS for short. A real-time OS is designed for systems where timing is critical. That means the system must respond to inputs or events within a fixed and predictable time frame. Think of systems that control aircraft, medical equipment, or industrial robots. If a machine sensor detects overheating, the system must react immediately. Any delay could cause damage or danger. Examples of real-time OS include RTLinux, QNX, and VxWorks. A real-time OS doesn't just focus on speed, it focuses on predictability. It ensures that every task is completed within its deadline. There are two types of real-time systems: hard real-time and soft real-time. In hard real-time systems, missing a deadline can lead to catastrophic results, for instance, in a pacemaker or flight control system. In soft real-time systems, missing an occasional deadline is acceptable, like in video streaming or online gaming. So RTOS is all about reliability, precision, and guaranteed timing. Finally, we have smart card operating systems. These are tiny OS versions designed for smart cards, those small chips you see on credit cards, SIM cards, or ID cards. Even though they're very small, these chips perform important security functions, storing data, encrypting information, and authenticating users. A smart card OS must be secure, compact, and tamper-resistant. Examples include Java Card OS, MULTOS, and proprietary SIM OS. For instance, when you insert your SIM card into a phone, the smart card OS inside the chip authenticates your identity with the mobile network. It handles encryption, verifies access, and stores secure data like contact information and network keys. Despite their size, these OS are designed with advanced cryptographic features to ensure privacy and data safety. So, if we take a step back and look at the big picture, we see that operating systems exist in all shapes and forms, from gigantic mainframes serving global banks down to the tiny chips inside your credit card. Each type of operating system is built with a different purpose in mind. Mainframe systems are created to deliver rock-solid reliability and handle huge amounts of work at once. Server operating systems are designed to stay stable under continuous network activity and manage many users smoothly. Multiprocessor systems take advantage of multiple CPU to speed up tasks and improve overall performance. On the other hand, personal computer operating systems concentrate on giving everyday users a comfortable and flexible experience. Handheld devices bring everything down to a smaller, more efficient form, making sure smartphones and tablets run apps smoothly while saving battery life. Embedded systems, along with tiny sensor node operating systems, are made for very specific tasks, often in small gadgets where low power use and simple, precise functioning matter most. Real-time operating systems are tuned for moments when timing is everything, making sure critical actions happen exactly when they need to. And finally, smart card operating systems prioritize security above all else, protecting sensitive data inside devices like SIM cards, ID chips, and bank cards. That is it for this video. See you in the next one.